Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. In the 6th International Conference on Industrial, Mechanical, Electrical, and Chemical Engineering 2020, we would like to present our paper about determination of VAR compensator placement for system stability improvement on Java Bali network. The authors in this paper are Adhi Apriyanto, Akbar Virgiawan, Henry Pariaman, Muhammad Hisjam, and Nanang Hariyanto. First, we want to explain about Java Bali network. Java Bali network consists of two levels of transmission line, 500 kV and 150 kV. Java Bali network has five regions. Region 1 and Region 2 in western of Java, Region 3 in central of Java, and Region 4 and Bali in eastern of Java. In Java Bali network, there is center of power generation in eastern of Java and center of load in western of Java. This condition causes power transfer up to 3000 MW from eastern of Java and to western of Java, and cause under voltage in western of Java. Under voltage occur in peak load and over voltage occur in low load. To solve this problem, first solution is maximize power supply from power plant. But unfortunately, the capacity of power plant is limited. So we need second solution. Second solution is VAR compensator installment. VAR compensator are SVC and STATCOM. The new problem are where we must install VAR compensator and how many capacity required of VAR compensator. In this paper, we use sensitivity analysis. Sensitivity analysis is the study of how uncertainty in the output of a mathematical model or system, numerical or otherwise, can be apportioned to different sources of uncertainty in its output. We use four parameters for analysis. First, voltage score. Second, bus voltage sensitivity score. Third, for power angle sensitivity score. And fourth, geographic location factor. First parameter, voltage score. To obtain significant improvement, VAR compensator should be placed on the buses having severe voltage problem. To assess the level of voltage problem of each bus, to determine the voltage index, we use equation 1 and equation 2. Parameter 2, bus voltage sensitivity score, dQ.core. Bus voltage sensitivity factor shows the influence of reactive power injection at a bus to voltage change at that bus. By placing VAR compensator at bus with high bus voltage sensitivity factor, it is expected that the compensation can be done optimally to provide improvement to overall system voltage performance. Furthermore, buses with high voltage sensitivity are located around locus of critical point of dQ.core. Therefore, placing VAR compensator at those buses will increase voltage stability. To determine the voltage sensitivity index, we use equation 3. And the parameter, power angle sensitivity score. Power angle sensitivity factor shows the influence of active power injection at bus that contribute to overall power angle change. Bus with high power angle sensitivity will be located around maximum transfer capability on delta P curve. Dot theta dot P is used to distinguish the placement of SVC and STATCOM. To determine the power angle sensitivity factor, we use equation 4. And the last parameter, geographical location factor. Geographical location factor is a method to optimize location selection based on geographic location. This factor is used because the reactive power injection is local, which means that it only affects substations that are close to the location where the VAR compensator is installed. If there are two or more bus candidates in close range based on geographical location, then the bus candidate with high score is selected. And then, how we determine bus candidate? We have three parameters: voltage score, bus voltage sensitivity score, and power angle sensitivity score. The total score is combination from three parameters. In this result, we use four scenarios. Scenario 1, wet season and peak load. Scenario 2, wet season and light load. Scenario 3, dry season and peak load. And scenario 4, dry season and light load. Bus candidate for STATCOM are represented by green area, while bus candidate for SPC are represented by yellow area. From total score, the several bus with the highest score will be selected. To optimize bus selected, bus candidate will be eliminated using the geographical location factor. So, the result of this paper, candidate for STATCOM must be installed in Ampra, CSW, Maximangando, Rancaike, Cepu, and Blingi substation. And candidate for SPC are Dukuh Atas, Lengkong, Cianjur, Ngoro, and Sumeneb substation. So, how do we prove that the simulation have a good impact? We can test with two parameters. Parameter 1 is critical clearing time. We simulate a system with disturbance at 50% lines. So they sort like this. By installing SPC and STATCOM, critical clearing time of buses in the system increase, thus improving system stability. Second parameter, we use the PV curve test. PV curve test is to determine the critical point of bus where the bus has collapsed. In the left set, PV curve at Ampra substation, and right set, PV curve at Sumeneb substation. From this graphic, we can conclude that the comparison of the PV curve before red line and after green line, the SVC STATCOM installation, it has shift at the voltage collapse point. With this shifting point, the maximum power transfer can be increased. So, from this paper, we can conclude the use of sensitivity methods for determining SPC and STATCOM laying location provide good result. The parameters used are voltage, bus voltage sensitivity, power angle sensitivity, and geographic location factor. Java Bali system require installation of STATCOM on Ampra, CSW, Maximangando, Rancaike, Cepu, and Blingi substation. While installation of SPC is required on Dukuh Atas, Lengkong, Cianjur, Ngoro, and Sumeneb substation. That is our presentation. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.